Well, there's readiness of our colleague, which gives me a prompt just to say a couple of more words to you. Well, first of all, let me just once again say that I'm so happy to have quite many of you right here inside this room. I can see there is some movement, there is some commotion ongoing. Please remember, this is not the only room for the rest of today. Room number 1, 8, and 9 are still active, and they're just giving you as much information as possible. Let me remind you also that this is Code Dive 2025, and I would like to kindly ask you to give warm applause to Nokia for bringing all of us right here inside these rooms. Thank you so much. Of course, we will remember about all our media patrons and everyone else who is supporting this event, also the radio stations, local radio stations, everyone, and we will remember it. There will be Eva coming onto the stage at the right moment. But for now, and I hope you don't mind and you still haven't had, like too much of that, I would like to also recall that, first of all, we are ongoing. Gašper is already with us, but I promised that there would be some tidbits coming from Wrocław. So actually, to all those of you who are inside and are watching us, let me only remind you that Wrocław is famously home to hundreds of small bronze dwarf statues. They are scattered all over the place, all over the city. Actually, I lost the number, of them just many years ago. What started as a political protest symbol in the 1980s was somehow commercialized and turned into a kind of treasure hunt, not only for locals, but also for people who come to Wrocław and want to take a photo with one of them. And actually, this little gentleman is our Nokia's own, called Nokiusz. So maybe, I don't know, some warm applause for Nokiusz for a moment. Thank you. You see, Nokiusz, we have very nice people inside the room. He doesn't speak. Anyways, but there is a person who speaks and he's ready, so let's not try to stop him. He is an ecosystem engineer at Citadel Securities, where he tends, as he says, the code biome and cultivates clean systems. So he co-chairs of SG4 networking. He's deep in C++ contracts, profiles, and whatever else needs untangling. He got his start on Amazon's search engine, where he worked with legends such as Alex Stepanov and John Kalb. And this is where his C++ standardization journey took root from. So now it's a tricky part. His cat's name is, just watch out, Old Man Terror Zluci Wilson, aka Oyabun. Don't ask me, please, but they told me that we checked, and this does not amount to animal cruelty, which we're going to check right now. Well, is there a cat somewhere? Well, probably not. Anyways, we're going to tell it to you somehow later on. Hopefully the cat is there. Is he?
At home.
At home. Okay, good. Wherever you are, cat, please just watch us, because the brilliance is deploying in 3, 2, 1. Make some noise for Gašper Ažman.
I don't think I've ever had a screen this big. Right, yeah, about the cat. The cat is his own. But he's also the local mafia boss, so that's why he's Oyabun. But these days he's retired, so it's okay. Right, so today we're going to talk about how do we prove procedural programs. We've had a lot of talks this morning about how we're going to make the ecosystem suck less and how to give people tools to statistically make their programs have less bugs. And that's super valuable. And the issue is that it doesn't quite get us far enough for some applications. So we are trying to do something more, to which they've hyped this up super much. And I have to tell you, I'm sorry, but as of this time, this is vaporware. It's still research. But let's hope that it actually lands in a tool chain and not a static analyzer in some near future. So that's basically what we're trying to do. First of all, I'd really like to thank a few people, because when you're researching things, there's a lot of free work. So first, I want to thank Codive and Andrzej, who made sure that this track happened and invited me and so on. So thank you. I don't think I'd have made this talk without you. I need to thank Lisa, Isidoros, and Joshua. We've been meeting weekly, trying to figure out how this all would work for the past few months. Lisa's been doing research on this for the last at least 10 years. I think more like 12 or 14, I don't even know. She's been writing talks about this for more than 10 years. And you're free to watch them online. I would really recommend them if you're interested in the space, but they are dense and it's work in progress. So, you know, and I want to thank Citadel Securities. This talk they had nothing to do with other than being very happy that I'm doing this on my own time. But they did sponsor me coming here. And so I do think that they're actually a super awesome employer, and we are hiring, so you should apply. Yeah, so what I want to convince you of today is that we all already prove programs. Otherwise, they wouldn't work. The issue is we don't do it rigorously, and we don't write things down. So how do we usually prove programs? We do it part by part and aspect by aspect, because we're humans and our brains are small. What do I mean by part by part? Function by function, class by class, module by module, subsystem by subsystem. We build abstractions because abstractions up to a certain size fit inside our heads, and then they stop. And so we need to break things down. Like, if you think about it, you don't need stud vector. Like, you could learn what stud vector does, and this is what they used to do in C and still do in C, right? Like, they have this array, and then they have functions that resize it, and the problem is it's very difficult to reason about that code. What do we mean by reason? We mean prove correct, right? Like, you need to convince yourself that your code works before you ship it. You do prove your code. We use abstractions to make the work easier of proving the code. What do I mean by aspect by aspect? So let's take something like studsort. We can look at its correctness, I guess. Thank you, Andrzej, for introducing this field way better than I'm going to do in this talk. What are we trying to prove right now? Like, is it that the implementation can or cannot reach undefined behavior? That's one aspect. Modify anything that it shouldn't. That's the example from Timur's talk where he said, can pushback print? Is it allowed to? Can it do anything untoward with the input? Like, we don't expect sort to do anything other than move things around, and if it does, it's probably incorrect. We also can ask ourselves, what's up with the result? Is it in fact ordered? That's part of correctness of sort. Is it a permutation of the input? Like, if the sort could, in theory, just copy the first element all the way along, and yes, the output is sorted, but it's not what you wanted. Can the output be different based on the environment? Like, maybe studsort runs a rand function and, you know, is deliberately unstable because it hates you. In fact, some hash table implementations literally deliberately run rand on construction to protect from some security vulnerabilities. So you will get a different ordering of your items every time you run the program, right? So sometimes you want to do this. The thing about proving programs is that it's fundamentally about trust. Like, we want to trust that our code does the right thing. And we are forced to prove them locally because it doesn't fit in our heads. So what do we resort to as a crutch? Like, what do we use as our basic tool? We use locality. And where there is trust in locality, there's also responsibility, and if need to be, blame. Thank you, Lisa. Why does this matter? Well, because whose fault a bug is actually super matters, not just legally. Like, I'm not that interested in the legal aspects of this, although we will use legal terms later if I get to them. The point is localization of the sources of bugs. Okay? And localization, I mean to code. Because a bug is something you wrote in code. Maybe it's an omission in code, but it's still, part of code. So whose fault is it? Well, the worst part is it's this neighborhood. So when I say neighborhood, I mean a function, a class, something that you reason about in isolation, right? Something that has an interface. It could be the fault of another neighborhood, such as if they passed you an input you said that you don't support, that's their fault. You could also be calling a function that promises to do something and then it doesn't. It's the fault of that function. It could also be outside interference, like some other thread scribbled on your memory. That's not your fault. That's the fault of that other thread or the part of the program that gave your memory to that thread. Or it could be unclear. This part, it could be unclear, is what Andrzej was talking about in the previous talk, where if you put annotations on your functions, if you describe what the function's interface is and what its contract is, you reduce the amount of unclear. Because unclear is really the misunderstanding between what the function is promising and what the caller expects. And here, I mean, by saying function, I mean neighborhood, and like it's research, okay. So let's get through some examples. So a bug in a dependency, like the very worst kind of bugs are hardware bugs, because they're not even in C++. Right? Like there was this floating point bug in early Pentium processors with fdiv. So you divided, and for some inputs, the division result was just incorrect. It just gave you garbage. It's clearly the fault of the CPU. Like you asked it to divide two floats, and it gave you garbage. Like what? A correct algorithm, like you wrote the correct algorithm and you ran it on a buggy CPU and it produced wrong results. The fault is with Intel, right? You remember this slide from earlier from Timur? The point of blame is to say, if we proved our code, the yellow bits, it's not that that code has no bugs. I mean, it's not that that code can't hit UB. It's that it can't hit UB in contract. Right? And so the idea is then, if we check on the boundary somehow, then we don't have to be checking inside the yellow bubble because we can prove it. I mean, this is like a step extra rigorous, right? Like ideally, we can get a lot of benefit by just runtime checking a lot more things, but we want to check as little as possible if we can guarantee correctness, right? So let's take an example. Let's say a bug in the caller, you call stud sort and you give it plus as the sorting, as the comparator. It'll happily do it. But the result ain't gonna be what you expect. That is clearly the caller's bug, right? The comparator is not transitive, and sort says it better be transitive. The thing is, this is not something sort can check, right? Like if you gave it a bad comparator, how is stud sort gonna check that it's a bad comparator? Like that's clearly a contract violation. Another bug in the caller is incorrect stability guarantees. Like, what if I call stud sort on some shared memory and some other thing is scribbling on the memory while sort is working? Clearly not the fault of stud sort. Stud sort says, I better have exclusive access while I'm dealing with this thing. And you didn't give it that. Like, this is also something sort can't check. This is not something sort's contract can check. We need, like, and this is kind of in the broader category of stability guarantees and immunities, which we'll get to. This clicker, yeah, okay. Okay, so what do I mean when I say unclear, right? Like, better have an example for that. So we see an f takes a pointer, dereferences the pointer and returns the int. And the caller calls it with nil pointer. So some code bases have a convention. If you're taking a pointer argument, it's never nil. Some code bases actually have this convention. Other code bases do not have this convention, and so a compiler cannot in general give you a diagnostic of whether this makes any sense or not. I mean, assume that these are not like in the same compilation unit or something, right? However, I can make it clear. I can make it clear two ways. The first fix is I can put a precondition on f, and then, because the pre is exposed in the header, when compiling the body of the caller, the compiler can say, oh wait, I'm seeing there's a precondition here that says this function f is going to dereference p. I shouldn't let you do this. And it should be able to issue a diagnostic. This is why I'm saying the top thing is not a bug. You said you're going to dereference p. Now, why am I saying, like, okay, so sure, I'm calling it with nil pointer. This is like another aside. Nil pointer is the easily diagnosable case of this being wrong. But what star p there is really saying is not, is this a nil pointer or not? It's, is this a valid object of type int? It's stronger than not a nil pointer, right? And so here we come to how the hell do we spell these things so that both programmers know what it means and the compiler knows what it means, and we ideally don't have to invent a new language because we already have a definition of what star p's preconditions are. Like, dereferencing an object better be it better be true that there's actually an object of the right type there on the other side, right? So we can say, well, if I write a precondition, and I know that there's this comma 1 over there, and I'm using double parentheses, so what the hell's up with that? Preconditions, the way they're specified, right, is like if a precondition returns, if the precondition predicate evaluates to false, then the program is buggy. But here, I'm saying, no, this precondition is going to evaluate to true. That's the comma 1 over there, right? I'm using the comma operator. But the other expression that's in there is evaluated, and it has preconditions. In this case, they're preconditions that the abstract machine understands, as in there's a valid object of type int over there. The preconditions of a precondition assertion are the preconditions of the expression in the precondition assertion. That's kind of obvious. And they're also exposed in the header. They have to be. So clearly, this is good enough for static analysis. This is good enough for proof, and I didn't have to invent any new syntax. That's pretty nice. So this is how we can fix it one way. This is how we can fix it the other way. I can say either pre is a nil pointer, either p is a nil pointer, or I'm going to dereference p. This is also a completely fair thing to say. I might have the comma in the wrong place. No, I think the comma's correct. Anyway, what this is saying is that f has a bug because it forgot to check for nil pointer in the body. Like we said, our precondition is this could be nil or it has to be pointing to a valid object of type int, and then we forgot to check for nil pointer. Obviously, it's f that has a bug, and the caller is perfectly within its rights to call it with a nil pointer. Okay? Like, if it seems obvious, it's because it is. If it doesn't seem obvious, then you're probably seeing some really, really deep implications, and you should feel proud of yourself. So the compiler should be able to diagnose the above bugs at compile time, right? And this is what we mean but when we say we want to be able to write down proofs for our programs in an automatically checkable way. And like, if I have to teach you a whole new language to do that, I have failed. Everything that we want to prove about C++ programs is expressible in C++ because those are the only things you can write. That's a really, really subtle thing that's actually a topological consequence, and that's Lisa's PhD from a long time ago. And it wasn't about C++, it was about category theory. But it follows, like C++ is a category and like it all works. But anyway. This is also why I said this is vaporware at this point. Like, we're thinking about it. We're still figuring out how to actually do this. Isidoros is actually working on generating the proof checker for your program from your program source code. It's like a straightforward linear transformation and for a given value of straightforward, which it is not. But, you know, like it is linear in your source code. So that's very nice. So you also should remember this slide. And at this point, it should be obvious that where we want to be is in annotations. Like, we want to give enough annotations for the compiler to be able to reconstruct the proof that was in your head when you wrote the code. And then, because we have to do it piece by piece, aspect by aspect, we can't do this globally. There's too much C++. Like, LLMs will help, yes. But there's a lot of code to review, and they're wrong in quite a lot of cases. So, you know, there's going to be an indefinite transition period of probably something like 50 years before we get all the code annotated, right? So we also need this bit on the boundaries so that we can check the things that aren't annotated, whether they meet the preconditions. And some things are checkable and some aren't, and I'll get to which ones are and which ones aren't. So what does correct mean in, you know, this case? It's like, it broadly means I'll do the right thing, provided my preconditions code and the functions that I'm calling aren't lying. Or at least their interfaces aren't lying. That's what being correct for a neighborhood means. Andrzej was talking a lot about what correct for a program means. But that's the whole thing. What correct for one neighborhood that has a contract both at the top and on the bottom, because it's calling some things that by itself have a plain language contract, if you will, is this, right? If their contract isn't lying, and if I get input that I understand, I will do the right thing. That's what correctness means. And in every other case, I can point my finger at who's wrong. And it better not be me. Like, that's really the other way to state this. I'm correct if for every bug that occurs in my body, I can point to somebody else and saying it's your fault. Sounds very much like human, you know, societies. Now, when we're talking to each other, like, the blame game isn't always constructive or useful because the person to blame doesn't necessarily have the capacity to fix the thing that they screwed up. But this is code. This is not people, right? The point is, where's the bug? That's where we need to fix it. Okay. So, of course, if you extend this all the way, like if all the neighborhoods are correct, then we have a correct program. QED, we're done. Hooray, we can all go home and everything's fine. And I will probably wake up the next day and realize that this was all a dream. Oh yeah, I do have this for aspects under consideration. We will not prove all the aspects of a program in one go, right? Like, today when most of the talks were going on, like Andrzej was really the only one who went all the way to let's prove behavior correct. The rest of the community is exerting a lot of pressure in lifetime and type safety correctness, and not so much in the algorithm does the right thing correctness. The problem is these things are all intertwined to some degree or less. And so you need to prove one aspect, and then you can prove another aspect, and then you realize that to completely prove the second aspect, you actually need to prove that some algorithms are correct. Like if your integer addition doesn't do the right thing, then you probably can't do pointer arithmetic kind of thing, right? Like things impact each other. Okay, so non-local proof is really hard. That's kind of the core of the issue. Proof is really laborious. Like when we're writing code, that's the hard part, convincing ourselves we did the right thing. And when we change code, we mostly redo the proof for only the code that we changed, but then we usually don't redo the proof for all of the other code this touches, because it's annoying, right? And a lot of the time, the issue really isn't so much that it's annoying, because that's just laziness and we're not lazy. But what's the impacted code, right? Like it's all the callers of the function and if what we changed was a function, and their callers potentially, and also their callers, and like then the neighborhood of things you need to reprove grows kind of exponentially like an expander graph, right? It could also be like the other end of a queue, like your function is interfacing with some queue, like whoever has the other end better, their proof needs to be rechecked, because you might be sending something that has a slightly different layout. I don't know. Other tools that touch the same data, it's not even in your program. Like you dump some file and all of a sudden it has a different layout, and everything that loads that file needs to be reproven, etc., right? Like an example I have is, let's take a random retail website, right? And the marketing department says, we want to do a 10% off on all sneakers promo. And then the developers go, okay, we're going to need to change price calculators, and we're going to need to fix indexing because they want to filter by price search, and that impacts ranking. Accounting is going to want to track the rebate separately from the actual sales price so that they know how much this cost them. We also need some monitoring changes so that we know if this particular promo is working all the way. We need to change the UI because it needs to display not just the 90 euros, which is what the pricer would say, but it needs to also display the previous price crossed out. And who else knows? Like you have to like literally do a whole like analysis of what code needs to be reproven because it got touched by somebody saying we want to do a 10% off promo, right? So we're totally doomed. Because proving code is laborious and manual. But what if it weren't? Like we had, I don't know, maybe like 20, 30 years ago, we had the same argument about automated testing. Like, oh my God, testing code is so hard and laborious and manual. What if it weren't? Like, what if when we write code, wrote a totally separate piece of code that tests our code? Wouldn't that be cool? Well, as an industry, at this point, we have pretty much unified on the view that unit tests are not optional. In other words, when you write code, you also are supposed to develop an automated system that tests it. This is now commonplace. Why not proofs? Might take another 30 years, but it's worth it. And by the way, this is not just for C++, right? Like this is theory that's applicable to most programming languages. It's just we're doing it on C++ because it's worth it. So the current tools for code reliability, right, are testing, runtime checking, which we've spent all day on. We also have strong types, like that's one proof system that's already integrated into C++. I'll talk about them in a little bit. We also have static analysis, which we've also talked about. And a part of static analysis are proof systems. So what do I mean? Okay, so testing. We've got automated testing, we've got manual testing. What tests do is check that the proof that was in your head connects from the start of the trace, if you recorded the trace of the test through your code, right? Connects from the start of the trace to the end of the test. But it checks one trace per test. And it says, okay, yeah, I recognize this trace. This is okay. Or it says, this trace seems sus. I do not like it. Test fails. Tests act like checksums. They build confidence in our code. The issue is comprehensive testing, as in checking all traces, is unaffordable in most cases. Like we check the interesting ones. Well, how do we select the interesting ones? I have a feeling that this is an interesting trace. This is how we check the interesting ones. But it works, because we care about our work and we think very thoroughly, and then we prove to ourselves that the test harnesses that we write are sufficient. And sometimes we fool ourselves. Okay. The issue is that tests, when we change our code, check the same traces that they were checking in the first place, right? Which means that they find things that no longer work the same way, but they don't solve the problem of what are the other things we need to fix because they shouldn't be working the same way. We are adding a feature. We're changing the system. They don't help us close the boundary of things we should fix. They just show us things that changed. And then we have to decide, is this a good change? Is this expected? Or is this not expected? So they don't solve the boundary problem that we talked about before, right? Runtime checking, we spent a whole day on it. They act on the current program state, and they check if the proof in your head connects from start of program to here for the current trace. Here being the place where your annotation was, right? They rely on data available locally. That's very important because we don't have a global store like the JVM does or something. And they can't check immunities. As in, they can't check that everybody else in the world will not write to this memory. Or they can't check that, you know, something is not going to change the active type that's stored in this piece of memory. They can check things that are locally available. And that's a lot, but it's not what the safety and security people want. They want like a total global proof, right? And often they find issues too late. As in, if you didn't have a test that failed, your assertion will find the issue in production, which is better than not finding it, but it's not shift left enough for some use cases. So I want to do better. Like that's the point of research, right? Where did we? This went way too far. Yeah, and again, they act on traces, right? Okay, so strong types. They're a proof system. Types in C++ are Turing complete. It's great. We have proof systems at home. Why are you working on a new proof system? Well, because I actually built an incredible strongly typed system. Like it works amazingly. It was such an investment. It was so worth it, but like we should be able to do better. like for anybody who's not familiar with strong typing, the tenet is only plausible business logic should compile. And you introduce more and more and more types until that's true, right? So that means you encode runtime properties that are true only for like a little bit of the code in a type. You check it on construction, you know, and then types carry the properties around, and then you have types like sorted vector and unique vector and so on. This is really, really good for code that has to be correct. It's an investment. Like, it has drawbacks, right? The drawbacks, well, the strengths, sorry, they are available right now. They also do solve a lot of the forgot to change a place problem, because when you change your domain type, its interface is so bloody constrained that the thing doesn't compile until it's correct. You made the intended change in one place, and then the whole thing doesn't compile for like a week, right? But the thing is, that week, every 15 seconds, the compiler told you forgot to change this bit, and you forgot to change that bit, and you also need to fix that bit, and you need to fix that bit. You know what can do that really well? LLMs. So that suddenly has a much reduced cost, but still super important. Doesn't solve the other problems. It can model some immunities, right? Like if you have completely immutable types, then that can model an immunity from modification. Because ain't nothing gonna touch an immutable hash map, right? If it's sometimes mutable and sometimes not, then strong types can't solve that. Shared pointer somewhat solves the immunity from destruction. Sure, you're not going to be writing into uninitialized memory, but let me tell you, you know, like this strong typing system that I was talking about? The only actual bug we had was because of shared pointer, because we kept an object around too long. We should have crashed. It would have been better. They also have a problem with orthogonal properties. Like, okay, so sorted, let's say it can take a unique vector because you have enough overloads. Like, I'm not showing them all because slide. A sorted of something will give you a sorted that, right? So obviously, sorted of unique vector gives you a sorted unique vector. A unique of anything that is uniqueable will give you a unique sorted vector, and these are somehow not the same type. I have to tell you, this does wonderful things to your debug symbols and your code generation and bloat. It's not fun. Also, the smart people in the audience will have noticed that this is the same as a flat map. A flat set, which, you know, it would be nice if we had type normalization machinery in C++. It would make type systems a lot easier to program, and we did put one in, but again, it's another layer on top that's annoying to work with, and nothing else works with it. Which is the next point: interactions with the rest of the ecosystem are a problem. Because like, if you have a really strongly modeled domain type tree, I guess, set, nothing else works with it because it's yours. So you're stuck translating from like some libraries types to your domain to another domain. It gets really laborious, and it requires runtime checks every time. Okay. You also need efficient variant subsetting, which we don't have, because you want to model state machines as variants of actual state types, right? And state machine matrices are usually not dense. And so, yeah, it's got issues. So we have also traditional static analysis, which, you know, probabilistic detection of common wrong patterns means you detect common wrong patterns. This is what Andrzej was talking about when he said they learned about stud string and now they know this pattern, right? Like, it would be nice if you didn't have to teach a tool about every friggin' type separately. they also focus on locally reachable undefined behavior, which is great, except for the fact that they have a really high bar for false positives, which again, Andrzej was talking about. Widening the window where they look is computationally extremely expensive. Like if you tried running some static analyzer on like your whole company source code, you could probably just come in next Tuesday, right? So how do we prove our programs? Again, we use abstractions. Abstractions have interfaces, and interfaces define bugs. Like they define what a bug is. Abstractions have never been about readability. I know people go on and on about code readability. That's not what they mean. That's what they think they mean. They mean provability. Like, how easy when I'm reading this code is it for me to convince myself it's correct? If I need to work for it, the code's not readable. But it's not really not readable, it's not provable. Right? The reasoning about code is about provability. Like, in the usual, I will sit down and figure out how it works sense. And so there have been a lot of proofs systems for procedural code. I'm not discounting them, but the problem is Dijkstra did not go far enough. His predicate transformer logic was a really big leap forward, but it's too tight. Like, it's expensive to evaluate, for one. You have like the tightest preconditions and the loosest preconditions functions, and then you union those things, and that gets you in your interfaces become really jaggedy. Like, no human thinks about interfaces that way. Like, when you get an interface that's computed out of your implementation, you effectively get what Hiram's law says about your function, which is not how we think about functions. Like, implementation is like 3/4 incidental complexity and like 1/4 of actual complexity, right? We don't want to expose the incidental complexity in our interfaces because that's how we reason about programs. So we use a lot of what I call precondition smoothing. So let's say we have this function. It's from a video game that totally exists, and we want to, move Mario. And we have the current position, and we get the delta, and we compute the next position. It's deliberately very, very simple. It's for a simple frame. We don't even divide anything, right? What are the preconditions for this function? Well, obviously the precondition is that the additions over there don't overflow, right? That's basically the only precondition for code as written. But that's not what the preconditions in the game are. The preconditions in the game are actually this. Current is non-negative in less than 256. That's never going to overflow. The level can't be more than 256 long, right? Like, you're never going to move Mario to 256. You're never going to move it into -1. There's never going to be overflow in this situation. And this creates this nice little neat box that humans can reason about and say, okay, well, if I call this function outside of this, then it's obviously a bug. Like, I got into a position that's outside the level. That makes no sense, right? And so this is what I mean by precondition smoothing, right? Like, before, in this case, we had our preconditions that were like sort of, circular. Like, they were in a circle shape, like x and like the current.x and by.x are interdependent in this precondition shape, because the second they, like if one's one less, then the other can be one greater and so on. Nobody can reason about that, and we don't want to. So we make our lives easier. And then suddenly, even a proof checker can be like, well, this is a nice convex region, great. So this is the anthropic principle of program proof. Like, human brains have a constant space working set and very limited time. We ship programs we can reason about, because that's the only programs we, care to ship because we at least think they're correct. Therefore, proof sizes are limited by, O of code. Like, we have to prove code in linear time in our heads, otherwise we can't ship the product. Some cases get a little small and polynomial-ish and so on. Like, forget those things. Like, they just think whole program. So it should be the case that we should be able to teach a static analyzer to do the same thing. And I want to say that, like, this is clearly a subset of possible programs, but it's the subset we're interested in. And so this is what I term human provable programs. Like, this is why the halting problem is not our problem. Like, if you're in a halting problem situation, go home, right? Like, you can't ship that product anyway. We care about things that end. So that's why precondition smoothing is the absolute main important thing. This is why we have hope. So how do we do these global things? Because I said proof needs to be local. And obviously lifetime proofs are a somewhat global property, at least how you would imagine them, except for the fact that they're not global, they're just non-local, right? Like, lifetime doesn't escape from the component that created it, and then there's a cone of things that get to see that object, and that cone has boundaries, and it's usually not the whole program unless it's a global variable or something like that. But at that point, the proof for lifetime is really simple, right? If it's a global variable. So the point is, how do we connect this boundary of an object being alive so that, like, just enough so that proofs can be carried out? Timur, showed the slide where he said, well, the bottom one is not diagnosable at compile time. That's what we want to diagnose. And so what we do is we turn non-local proof to local proof by having annotations. So we've got f. F is the same as on Timur's slide, except for the fact that we say in our precondition, I'm going to dereference p. Make sure I can do that. You're my caller. It's your fault if you don't. And then mid, the middle function, says, well, I don't have enough information either to ensure this, so I'm going to expose that too. I'm going to say, I know that f is going to do star p. I'm not going to do star p, but I need to expose this. And then top, that calls it with a nil pointer, has a diagnosable bug because it sees the precondition on mid. Now, the obvious problem with this approach, while it obviously works, is that if you change f, then mid has incorrect preconditions. Because mid didn't really mean star p in this particular story. It might in some other story, right? What mid meant was this. Whatever f of p needs is also my precondition because I can't check it locally. But why couldn't you do this? Like, you can, right? Like, the precondition for f is in the header that declares f, which means mid's declaration in its own header just re-exports the precondition that f declared by saying, you know what, I'm just invoking it in my precondition. That's fine. Obviously, the preconditions of mid's pre are the preconditions of f. And so then, the final bug is also diagnosable. This is very simple. If we did this, static analyzers can do this tomorrow. Right? This is not new technology, it's just a new way of putting things that already work together. So we said that interfaces define bugs. Some interfaces can also detect bugs. Like the lifetime stuff you need to prove. But, you know, for lower bound says is sorted of range, that's my precondition. It's checkable. It will break the time complexity of lower bound if we actually wanted to check it, because it's a linear algorithm. It's actually not a linear algorithm, but it is here. Never mind, the advanced talk. But is sorted looks like this, right? So we take a range begin, we copy the iterator, we take end. If we're done, we're done. And then we have this can't check lifetime here line, right? We dereference the iterators. And we're getting a span. Somebody else needs to guarantee the lifetime of these things. That's a precondition of is sorted. But we don't specifically need to expose it as a precondition because is sorted is inline. Now that's a word of power that means a little bit more than what inline means in C++. This inline means you have to process this definition when you are looking through preconditions, because you need to extract the preconditions of every statement in here, which is really annoying. So ideally, we have to expose this if statement for every element on the precondition of is sorted, and then that can be proven separately, and then we don't have to have the whole algebra. I've thought it through, Lisa's thought it through. There's no time to do it here, sorry. So if I wasn't hand-waving enough by now, I have to start hand-waving even more. I'm sorry, it's 10 minutes till closing. I wanted to have Q&A for the last 15, but like I need to get to the fun part. So C++ is a language for libraries, right? You know the whole like counted by stuff that Clang standardized and all of that? That should be a library feature. We should only standardize the, sorry, John. We should standardize the bits that deal with the abstract machine. Like integer operation preconditions obviously need to be part of the standard because you can't express them by yourself. You can't express the lifetime guarantees of pointer dereference. They're defined by the abstract machine. Like as in you can't express it in C++ code. They're expressed in the English of the C++ standard, right? They're defined by the abstract machine. But everything else we should be able to do in libraries. Like is sorted is clearly a library predicate. And the language needs to be C++, maybe with a few more like annotations. So the abstract machine provides the basic operations for built-in type, the starting and ending of lifetimes. It provides execution, so this is where we get threading primitives from and so on, and how memory behaves. So what should be built in? Locally checkable things like the integer overflow, and we've got the implicit assertions that Timur was talking about and so on. This is easy. Lifetime memory mutation races types things. As you remember from Timur's talk, that's all a caboodle. Like it's all interwoven. We have to know how to address those things as primitives. We can't talk about them in C++ code. And that's what 10 years of Lisa's talks are about. So making far things local, like I showed one example, the full talk is Lisa's what neighborhoods owe to each other, but Lisa loves placing emphasis on the word that you don't think is the operative one. That talk is actually about what kinds of things do neighborhoods owe to each other. Like, how do we describe this? Like, what's the algebra made of? What are the basic particles of it? Things that neighborhoods owe to each other look like these objects are alive. Like, I'm promising you they're alive, and they will be for the duration of your execution. Like, nobody else modifies this memory while you're using it. this end iterator is reachable from this start one, is a thing you have to promise, right? This collection is sorted, is a thing you promise, because you don't want to recheck it. This queue produces elements in sorted order. Like, how the hell are you going to check that? You have to read the queue to verify that. If you hold this shared pointer, its object won't be deleted. That is what shared pointer is about. It doesn't promise you anything else, which is a problem, but that is what it's about. This local variable will have the same bits every time you read it. That's kind of obvious, but that is what the abstract machine promises you. It promises you it will keep memory the way it is unless you write to it. Like, RAM is doing this actively every cycle. That's a duty it has. So the elements of proof are actually from Wesley Newcomb Hofold, who was a Californian legal scholar at the turn of the 20th century. And he was very concerned with a few more legal correlatives, but I'm only going to talk about the ones that apply to programming because I don't have a full talk's worth of time. So he was really concerned with the dichotomy between rights and duties. So if somebody has a right, somebody else has a duty. Like, if you have a right to a job, then the government has to give you one, even if there are no jobs available. They just have to make one on the spot and pay you for it. And of course, then getting a real job is quality of implementation, right? Rights and duties are particle antiparticle. When you create a right, you create a duty, and vice versa. So an example would be, I have a function, I declare a variable x, and the machine has the duty of maintaining the value of x, so that when you read it the next time, it will still have the value 2. And f gains the right that x will not change. These are tokens, right? And when we read x, yep, didn't change. We read it again, still didn't change. Okay, so what's the contract of assignment? The contract of assignment says, I need a right. Like, you need to give me back the right of this thing will not change because I'm gonna change it. If you still have that right, I can't change it. So assignment needs you to give it a right to change. So rights pay for rights. And then when assignment completes, this assignment is integer, so it's implemented by the abstract machine. The abstract machine, like, when you give it back the right for no change, the abstract machine annihilates its duty, does the thing it promised it would do, creates a new duty of maintaining the value 3, and gives you the right to 3. So that's the contract of assignment. And then the destructor consumes a right to the maintenance of stability of value and doesn't give one back. This is how that works. So we have another pair of legal correlatives, which are immunities and disabilities. These are not primary. They always trace back to either a right or a duty or another immunity or disability. They're like, they're also antiparticles, but they're like derivative antiparticles. They're like, and I mean derivatives really in like the financial sense of like, you can't have a future without an underlying asset, right? Like, but you can have a future on a future, not that, I mean, people do it, but it's a little weird, but here it actually comes very handy. So what do I mean by immunities and disabilities? If I have an immunity, that means that from something happening, then that means that somebody else has a disability from doing that. Right? Like they are not allowed to do the thing because I have an immunity. So the example here is that the rest of the machine has a disability to writing to a variable while I'm reading it. That's race conditions for you. In order to read anything, you need an immunity. from writes to that variable by other contexts. That's the contract of reading. So I can read a value because I have an immunity from it being written concurrently. This is the same as saying any context that has a right of stability of the variable has a disability sitting on it. Like, why is that true? So if you have a right of stability, that means you can call assignment, right? But if I get to read the variable, that means that your right to assignment has a disability like a stone on it. That means you can't use it while you have that disability on that right. So I need to give you my immunity back somehow in order for you to be able to call assignment. And I really want to get to this slide. So is this like borrow checking? Like, that sounds very much like borrow checking, right? But no, it's actually a lot more granular than borrow checking. See, I have a mutex. And I have main. So let's go through here. We have a mutex M. We create it. What do we get when we call a constructor? We get the right of stability of the mutex, okay? We also create an integer with the value 5, and we get a right of stability of I, and we'll call that Ri, right? Now, I don't have syntax for this because this is still a research project. But I can put the right of stability of I into M. I give the mutex my right to stability. That means I can't call assignment, right? I also need to create an immunity disability pair for the stability of the mutex, my right to the mutex, which means I can't use that right. But I still have it. And I can make a thread, and I give the immunity for the mutex to the lambda that the thread calls. Now the log guard is going to obtain the right of stability from the mutex based on the fact that it has an immunity on the mutex. Right? Like, it gets to read the mutex because it has the immunity, and then it can get the right back out of it, which means it is legal for it to call assignment because it now has the right. And then it automatically gives it back to the mutex once the log guard, gets destroyed in its destructor. And then I have to call join. Why? Because I need to reclaim my immunity from the thread. And once I have the immunity from the thread, I annihilate it with my disability with the mutex. That means I can now destroy I because I got the right back. I couldn't destroy I before, which means I can't forget to call join, because otherwise I can't get my stuff back. And then, because I have also destroyed my disability on the R for the mutex, I can destroy the mutex, because that's what the destructor needs, right? And so that's the algebra that you need to go through here to do multi-threaded programs. And this is not borrow checking. This is just literally Hofeldian rights and disabilities, and it's a nicely counted algebra that you can just do. And you can communicate these tokens across communication channels. So is this ghost data? Yes, kinda. But do we need storage for these tokens? Not in this case. The mutex has actual real data. Like, the atomics that are in the mutex can carry this. Like, this is all symbolic. This is all symbolic evaluation. We're doing it as is. We can recover the ghost data from real data when we need it at runtime to prove things. That's not always the case. Like, if you remember the slide with the boundaries, we need actual data to keep around to prove things at the boundaries, because the other parts of the program aren't going to give it to us. But we don't need it in the proven regions. And why do I know that we usually don't, in a correctly annotated program, we don't need actual data to store ghost data, because a correct program, a human provable program, does not rely on luck for correctness. We have mechanisms that are real mechanisms that guarantee us correctness. We just haven't annotated them that they actually communicate the things. And that's it. That's really it. That's my recap. Thanks.
Absolutely. Absolutely amazing, ladies and gentlemen. Gašper, Ažman, it sounded like philosophy. I'm a humanistic person, so it sounded like a philosophy of code writing to me. So please give a very warm applause once again and say thank you this way. Okay, we don't have time. There is a coffee break, but I would count on you just to come to you and just ask questions if there are still any. So we'll just switch the microphones off for this time, but the Q&A can be happening just in front of the stage as well, just as it was in the previous cases. Once again, big thanks, and this was so nice to have you right here at Code Dive 2025. Please give some warm applause and thank you once again.